Hello, dear and valuable students, and welcome to Human Anatomy and Physiology Laboratory Manual. We're going to be doing the PhysioEx exercise. We're going to be doing exercise 5, cardiovascular systems dynamics, and we're going to be doing activity 1 of exercise 5. As you see, PhysioEx is divided into multiple exercises, and each exercise has multiple activities. And today we're going to begin exercise 5, cardiovascular dynamics, activity 1, studying the effect of blood vessel radius on blood flow rate. So as I mentioned to you in class, whenever we have an experiment, the first thing you must do is to always identify the independent variable and the dependent variable. As is in the court of law, the first thing that the judge does is to identify the plaintiff and the defendant, and then their witnesses. That's the first thing before beginning the case. So you also, before beginning the experiment, you have to identify your independent variable and dependent variable in the experiment. So studying the effect of blood vessel radius on blood flow rate. Obviously, we have two variables. So the blood vessel radius, that's a variable because it can increase or decrease. The blood flow rate is another variable because it can increase or decrease. Now, what variable are we talking about when it comes to blood vessel radius? Is that an independent variable or is it a dependent variable? We said that the dependent variable is what we are measuring, is what we are studying. Who is dependent on who? Is the blood vessel radius dependent on the blood flow rate, or is the blood flow rate dependent on the blood vessel radius? So the blood flow rate is the one that is dependent on the blood vessel radius. So as we increase the radius of the blood vessel, the blood flow rate will increase also, and it will increase exponentially. This is very important for you to appreciate. So the relationship is not 1-for-1. It's not like increasing the blood vessel radius by 1 order of magnitude is going to lead to an increase, a proportional increase of the blood flow rate by 1 order of magnitude. No, it's actually R directly it's actually F. When F represents for us the flow rate is directly proportional to R to the power of 4. So increasing the radius will lead to almost 4 times increase in the blood flow rate. And you will see that in this experiment. You will see that the graph relationship between the blood vessel radius and the blood flow rate will never be linear, because linear, it means it's 1-to-1 relationship. But here we have an exponential relationship that is 1 to 4 orders of magnitude. So the graph is always going to be curved. It's not going to be linear. That's very important. So now you have identified your dependent variable, and that is your blood flow rate. And it's a dependent variable because it is depending on the independent variable, which is the blood vessel rate. So remember, I mentioned to you in class that whenever you want to know the difference between two things, always begin with the similarities. I want to know the difference between the independent variable and the dependent variable. Let me first begin by outlining the similarities, and that is both are variables. Why do we call them variables? Because they can increase or decrease. Now, just because they can increase and decrease is not enough. I need to know their increase and decrease. Is it dependent on something? That makes it the dependent variable. And if it is independent, that makes it the independent variable. Okay, so let's click on activity 1. And the objectives are very important to just highlight for us. We're looking at the blood vessel radius because the formula is actually F, representing flow rate, directly proportional to R, which is the radius of the blood vessel, to the power of 4. So we're going to look at how increasing the radius will lead to 4 orders of magnitude increase in blood flow rate. And actually the opposite is also true. Dropping and decreasing the radius will lead to a 4 orders of magnitude drop in the flow rate. And this and then we're going to be studying how your autonomic nervous system, this is the changing of the blood vessels, this vasoconstriction and the vasodilation is controlled by your autonomic nervous system. It's an involuntary physiological process that is modulated by your autonomic nervous system. And it is out of your control, and it happens based on a supply and demand preference. So if you are running on a treadmill, your blood, your cardiovascular system discriminates. I know discrimination in law and discrimination in the social sciences may represent that there is some sort of form of violation of human rights, but in medicine, discrimination is your ability to discriminate. Were you touched by a sharp pin in your toe or your finger, or were you touched by a dull object? Were you touched by a piece of cotton, or were you touched? This is to test your nerves, your discrimination, your ability to use your sensory nerve properties. And here also your body is able, your cardiovascular system is able to discriminate that when you are on a treadmill running, all your other systems are not going to share an equal amount of blood. Obviously, your most of the blood is going to be shunted and given preference to your skeletal system because that's what you use. That's where there's the highest demand for blood supply, because the blood has a lot of oxygen, it has a lot of nutrients for metabolism, carbohydrates and fatty acids and proteins, and it can also remove all the metabolic waste that builds up in the tissue. So we need more of blood in a skeletal system, skeletal muscle system. But if you are laying down on the couch and watching some movie, then after you just had a meal and you just had dinner and you're laying down and watching a movie, then obviously your cardiovascular system is not going to be shunting all the blood to the skeletal muscle system. It's going to be shunting it and giving preference to your digestive system now, so that all of these intestinal tissues are able to perform their absorption, because now they are heavily involved in the process of absorbing all of these and digesting all of these mechanically and chemically digesting, using these enzymes to break down the carbohydrates and the lipids and so on. So I need you to appreciate that there is a supply and demand preference. Your cardiovascular system responds to which system in your body needs more blood, and it will give it the adequate amount that it needs for your survival and homeostasis. So in order to do that, to modulate, to give who gets more blood, who gets less blood, your body does that when the autonomic system regulates the radius. So we constrict the radius of all the blood vessels that are going to the systems that we don't need them to have blood, and we make vasodilation leading to the muscles because they are the ones that need blood, for example. So your cardiovascular system constricts by sending action potentials to, you have to know the structure of the blood vessel. The outermost layer is the tunica externa, or the tunica adventitia, and the middle layer is the tunica media, and the most innermost layer of the blood vessel that is intimate with the blood is known as the tunica interna, or the tunica intima. So because it's intimate with the blood. So how this constriction happens, it's the middle layer. It's the middle layer, the tunica media, that is rich in smooth muscles. We have different kinds of muscles in the body. We have skeletal muscles. We have cardiac muscles, and then we have your smooth muscles. So these are the ones that your autonomic nervous system stimulates whenever it wants to constrict the blood vessel, sending exponentials to cause, this vasoconstriction. So now we're just going to be looking at the concepts where controlling blood vessel radius, that is what enables us to give preference. Where should most of the blood be going? Which of the systems needs more blood supply to maintain homeostasis? And then there's the concept of the laminar flow, which is very important. Laminar flow is, imagine you have a blood vessel. This blood vessel is a tube. So let me go ahead and type laminar flow and see what diagram I can get. Okay, that's exactly what I needed. So what happens is in laminar flow, if we look at A and B, for example, and we see that both A and B represent for us two blood vessels. The blood that is neighboring the edges, neighboring the boundaries, that is intimate with the tunica intima, with the innermost layer of the blood vessel. Do you think that's going to be going fast? No, there is drag and there is friction. So that's going to hold the blood backward. It is the blood in the middle that is far away from the edges that is going to be fast. Now, what happens in vasoconstriction, you narrow down and you make the space in the middle even smaller. So that decreases the laminar flow and increases friction. So that causes an overall drop and a decrease in the blood flow rate, while increasing the blood diameter, the blood vessel radius would increase the space that facilitates for the laminar flow to increase. And so there's more blood enjoying laminar flow movement and less blood in friction. So the more friction out there, the less the flow. There are other factors that we will also talk about. Um, but you just and then this laminar flow is when we're going in order, and then turbulent flow, that is different. That represents something that has nothing to do with our cardiovascular system, because it's our blood, that it's our heart that pumps this blood. It is our heart that pumps and ensures that the flow is going laminarly. Okay, so now let us move to, so we're going to be having two beakers, a left beaker and a right beaker, and both of them are connected by a tube. So the left beaker is going to simulate for us the heart, for example, and then connecting them is going to be an artery that carries oxygenated blood that is rich in nutrients, carbohydrates, and these lipids, and also the proteins, and then that is heading to a muscle, for example, the biceps brachii muscle. And then it's going to enrich that muscle with oxygen and all the nutritional supplies for metabolism. And then it's going to be removing all the metabolic waste. Okay, so the blood flow is measured in what? Obviously, millimeters of mercury. That's the unit of pressure. I mean, how many millimeters is mercury going to move in that sphygmomyometer based on the, so that's a pressure. So that's how much pressure is forcing this fluid to move up in my cylinder and sphygmomyometer. That's definitely not flow. That's definitely not flow. Flow is rate. So rate is going to be, I'm looking at something per minute. I'm looking at, how much blood is flowing per minute. So that looks like the right answer, where I have milliliters of blood flowing per how many minutes. Beats per minute, that's also a rate, but that's for the heart rate. And then millimeters per minute. That's like speed. Okay, you know, this car is going 700 miles per hour. I mean, that's distance per time. That sounds like speed for me. So flow is not speed. Flow is how much blood is flowing per minute. That looks like the right answer for me. Okay, which of the following has the greatest effect on blood flow? Actually, all of them do have a very important effect. Obviously, the radius has the most because it's exponential. It's r to the power of 4. So if you increase the radius by 1 order of magnitude, that's going to increase the flow rate by 4 times. Please remember that. The relationship between, I hope they have something here. The relationship between uh, flow and radius. I hope they have F directly proportional to R to the power of 4. Yeah, there we are. Something like that. Something like something like that. But it's F, the flow rate is directly proportional to the radius to the power of 4. So if my radius was 2 millimeters to the power of 4, if I increase it, make it 3 millimeters, the flow is going to increase by 3 times 3 times 3 times 3. So it's going to be exponential increase. So that's very important for you to very important for you to appreciate. It doesn't mean that the length of the blood vessel is irrelevant. No. So the length of the blood vessel is also relevant, where the longer the blood vessel, the less the flow. That's why it's in the denominator. So these two guys here. So this looks like an N that represents the fluid viscosity. So the more viscous the fluid is, the less the flow. If you have water flowing down blood vessels and then you have blood flowing down blood vessels, obviously water is going to flow faster because it's less viscous. So viscosity is in the denominator, meaning it's inversely proportional to flow rate, and the length of the blood vessel is inversely proportional to the flow rate, while who else is helping in the flow rate is actually the radius to the power of 4. Actually, that means it is really significant. None of these guys to the power of anything. It's just the radius to the power of 4. That shows you it's really, really determining. And then this shows you delta P shows you that the gradient is like a pressure. So the more pressure gradient, the higher the flow rate. So if you look at the pressure gradient from the aorta, where you have the highest pressure, so blood is just leaving the heart. I mean, the left ventricle just contracted. All the blood is just rushing out the aorta. That's where you have the highest amount of blood pressure, right at the aorta. And then right when you get to the muscle where the blood is you are about to enter into the capillary, in the microcirculation, and you have your arterioles, that's where you're going to have really low blood pressure, because that is very far. So the higher the gradient, the higher the flow rate. The higher the gradient, the higher the flow rate. The higher the radius, the exponentially higher the flow rate. And then the higher the viscosity, the less the flow rate, and the higher the length, the lower the flow rate. It's very important to understand this formula conceptually. And then there is this other concept known as blood vessel elasticity. It's not in the formula elasticity, but this is a pathological concept. So remember, we're not just dealing with anatomy and physiology. So anatomy is the structure, physiology is the function. We're also going to be looking at the very important pathologies that happen with what goes wrong with the body when something's going. So for example, atherosclerosis and atherosclerotic plaque in this blood vessel, or maybe atherosclerosis or arteriosclerosis, where there is a defect or some sort of aneurysm or some sort of a fibrosis that disrupts
the elasticity. So that's definitely, so losing the elasticity of the blood vessel will definitely detrimentally affect flow rate. So the more elastic, the better. But definitely the one that has the greatest effect, exponential effect, is actually the blood vessel radius. So let's move on to which of the following would not result in a decrease in blood vessel radius. Obviously, vasoconstriction is going to decrease the blood vessel radius. A plaque that is in the artery wall is going to drop the amount, that it's going to decrease the room for the passing of the blood, obviously making the radius really small. Vasodilation is the opposite of vasoconstriction. So now you're making the blood vessel radius really wide. So that's definitely the wrong answer. Contraction of the smooth muscle in the arterial wall, that represents for us vasoconstriction. So let us now move on. The diameter of the blood vessel is the same as the circumference, no, 2 times the radius. The diameter is 2 times the radius of the blood vessel. So the diameter equals 2 times R radius. Okay, the opening of the blood vessel where the blood flows is called, the laminar flow is not an opening. That is just describing whether the blood is flowing in the middle or in the edges. And the lumen is that space. So it's the opening of the blood vessel where the blood flows. That makes sense. The tunic is the layer. The tunica adventitia, the tunica media, and the tunica intima. And then the valve, these are the varicose veins. These are the valves in the veins that prevent backward flow, And then they get defected due to obesity or pregnancy, and then blood pools and falls down and aggregates in these lower limb, making an engorgement, pathological engorgement and pooling of blood. And this is pathological discoloration, bluish discoloration of blood. So that's not the right answer. The right answer is definitely the lumen. So now let's go ahead and start the experiment. So here they want us to study the effect of the blood vessel radius on the blood flow rate, maintaining the following conditions. So we have to maintain the pressure. That's the pressure. We keep it at 100. The viscosity, we keep it at a 1. And the length of the blood vessel is 50. And then they want us to make the radius 1.5. Okay, so that's the radius. The more we increase it or decrease, that's very simple. So 1.5. And then we do start, and then that just shows you that there is a measurement of the flow rate. And that just simulating for you like how much blood is flowing for this 1.5 radius. And then we're going to keep increasing the radius, and it's going to measure for us. Later on, we're going to discover that, oh, the more radius I increase, the more. So now we're just going to be pretty much looking at this. We're going to be just discovering all of these facts that we have already agreed to, but now we're going to see them in lab. Okay, so now we're going to press on record data. We see that the flow rate when the radius was 1.5, it was 4, and the viscosity. So you can plug it in this formula. I mean, plug in the radius 1.5, plug in 1.5 to the power of 4, and then plug in the viscosity and plug in the length and plug in the pressure and so on. And then it tells you so that you can study the effect of the, okay. So the next step is to, what is the driving force for blood flow? Obviously, it is the pressure gradient. It is my left pump. Then we're going, it's telling us to start, start and then observe the movement. Observe the fluid to my beaker. We have to so okay, we have to refill. So now everything goes right back. Then we're going to restart again. So we're going to be doing this a couple of times. And in the end, we're supposed to make a plot. But just remember, because the relationship is F directly proportional to 4 to R to the power of 4, then it will definitely not be linear. It has to be exponential. That's very important for you to appreciate. Um, let's hurry up. How can it's gonna take forever? Okay. Let us now hurry up. Okay.
Now let's do. So what are we doing exactly? Are we increasing? Let's do another one. Were we supposed to increase so that you study the effect of the blood maintaining the following condition? Increase the flow rate to 1.5 by selecting. Okay, so we have done that. What should we do next? Start. Some condition, be patient. So we're now just studying that. Okay, so that's the same thing. So now let us now play a little bit with the radius. So we're gonna increase the radius by a couple of units and then plot that in the end. And then we're going to keep the viscosity constant and length constant because we're not studying that. We're not studying the effects of blood viscosity on flow rate, or we're not studying the effects of blood vessel length on flow rate. We're studying only the radius. So that's the only um, variable. These are not variables, these are constants. Viscosity is constant, length is constant. This is our independent variable. So let's do a couple. Let us now do two. Let's just keep doing a couple. Hurry up, I have to go before 10:15. Let's record data and then let's refill. So now we saw that the flow rate increased almost 4 times. So yeah, so it's R to the power of 4. So the radius went up by 0.5 millimeters. So 0.5 times, so this is like 25 times 20. So it went almost 4 times. So let us now increase it to 2.5 and start. You see the speed increases by 4 times the amount that we increased. Record data. Let's do a refill. Let's again do the 3, then start. You see, now it's by 4 times. You see the radius is almost 4 times the flow rate is almost 4 times the radius. Then we're going to refill. Then let's increase it again. Then let's start again. Then let's record data. Let's refill. Okay, I think we got the idea. Now let's plot everything. Data. So data will only plot for the experiment as described. So this is the flow. That's the dependent variable always on the y-axis, and then the x-axis is going to be the independent variable, and that is what we are changing. But what we are examining is our y-axis is dependent on the x. I mean, the more we increase, it goes up, and if we decrease, the y-axis value goes down. So let's click submit. Let's move next to record data. We have done that. We have done that. Okay, what do you think will happen to the flow rate if the radius is increased by 0.5? The flow rate will increase by 4 orders of magnitude. Okay, let's do next. We did that. We did it. How does the body increase the blood vessel radius? Smooth muscle contraction, definitely by contracting the smooth muscle where in the tunica media. Smooth muscle, I'm sorry, how does the body increase the blood? Oh yeah, I'm sorry, by vasodilation. So we constrict it, we drop R to the power of 4. It's actually, yeah, it's smooth muscle relaxation. Okay, submit. And then I'm sorry, I'm in a hurry, I'm trying to go. Do you think a graph plotted with radius on the x-axis and flow rate on the axis will be linear? No, it will not be linear, and that's the main problem we discussed it because it's R to the power of 4, so it must be exponential. Okay, and congratulations, you have completed the experiment. Submit. You have submitted. Okay. The variable that you altered in this activity was obviously the blood vessel radius. And the vessel radius and fluid flow are definitely directly proportional. The more exponentially actually proportional. Non-linearly proportional. They are non-linearly directly proportional. Exponentially directly proportional. Next. After a heavy meal, when you are relatively inactive, oh, I said that on the sofa bed watching TV, we might expect blood vessels in the skeletal muscles to be somewhat constricted, definitely, and the blood vessels, the digestive organs to be dilated so that, wow, they used the same example I gave in the earlier explanation. Wow, amazing. That is so nice. Thank God, that is amazing. When you increased the flow tube radius, the fluid flow rate, when you increased the flow tube radius, the fluid rate increased exponentially. You can see that in all of the data also. Explain how the body establishes a pressure gradient for fluid flow. So here you would say that the heart, the left ventricle would pump all the blood and the blood would gush out in the aorta and so on. Okay. Explain the effect that the flow tube radius change had on flow rate. How did the results compare? We have said that the flow rate would increase exponentially to the power of 4. Use that formula that we just discussed. Describe the effect that the radius changes have on the laminar flow. So if we have vasodilation, we increase the blood vessel radius, the laminar flow space would increase, so we'll have more laminar flow. But when we do vasoconstriction, we constrict the smooth muscle in the tunica media, we would have less laminar flow. Why do you think the plot was not linear? Because the relationship between the radius and the flow rate in the Poiseuille's equation is actually exponential. X straight. No, it will not be linear. It will be curved, and because it's an exponential relationship. Okay, we are done. Let me upload this on YouTube and see.